All right, now let's talk about if things bounce. Think about this. There's this falling pot. You catch it in your hands and you slow it down until it stops, and then you throw it back upward. So you have this impulse to stop it. You have another impulse to throw it back up. So two impulses. So, if you're standing there and this flower pot hits you on the head, yeah, that's probably going to hurt. But you know what? It's actually far worse if that flower pot bounces off your head because there's more force. Remember, it's like catching and then throwing it back up. There's two impulses needed here. So better if this thing just hits your head and breaks versus if it hits your head and bounces. So that's what karate, people do here. If they get their hand, they hit it hard enough, the hand bounces, they can actually apply twice as much force by doing that, by having their hand bounce back. Instead of, when you do, if you're going to do this, you want to make your hand bounce. You don't want your hand to just hit on the brakes and stay. Then, you're not getting as much force on it. And here's another example. They've got this, what this is, and we actually have one of these, and we'll show you this to you during class. But this is a dart, kind of a wooden thing, and it swings hard enough to hit this thing. If it bounces, it topples this thing over, and then you can make it so that it doesn't bounce, and then the object will stand up. And it's kind of interesting to see how it's the same object. You pull it back from the same distance and everything, but just the fact that if it's going to bounce or if it's not going to bounce makes a difference whether this block is going to fall over or not. Good example of this were water wheels back that were designed in the gold rush. The original ones were just flat wheels with paddles, and the water would hit, and they were very inefficient. So this guy named Lester Pelton designed curve-shaped ones, and where the water will actually come in and then bounce out, and that provided a lot more force. And actually, I think if you look at this picture, I think they went that way, so I think the picture is actually backwards from what it is. But regardless, the idea is the same, is that the impulse is greater because the water bounced. So the guy probably made more money off this paddle, off this wheel, than any of the people did searching for gold. Conservation of momentum. All right, the force or impulse that changes momentum must be exerted on the object by something outside the object. So if we want something to change the momentum, force that changes momentum has to come from outside the object. I mean, think about this. If we're talking about a basketball, if we're looking at the molecular forces, all the atoms, and they're bouncing around, the ball doesn't start bouncing because all these atoms are bouncing around. No, in order for us to get the ball to move, we've got to go pick it up and shoot it. Or what if you're in a car? If you push against the dashboard, does the car move? Do you get the car to move? Do you get it to go forward? No. You need an outside force in order for that to happen. Inside, that's inside the system. That's the forces are always balanced, and nothing's going to happen. Okay? If we look at this cannon, here's our cannon. Right now, this cannon has zero momentum. Nothing's going on. Fires the cannonball. If our system is the cannonball and the cannon, the overall momentum, this is going this way, this one's got momentum this way, and these are vectors, so if you add them up, you end up with zero, nothing here, just like this one. Because guess what? This is the system, and no matter what I do in here, if that's the system, I can't change the momentum. So it started at zero, it's going to end at zero. The only way that I could change it is if I came from outside, pushed it or hooked a horse up to it, pull it or something like that, then I would change the momentum that it has there. All right, so this is pretty much just telling you the same thing. Before I fire it, it's zero. After I fire it, it's still zero. No momentum is lost or gained. And momentum, like force, like velocity, like acceleration, is a vector quantity. And, you know, it's a vector quantity because mass and velocity was a vector, therefore this one's going to be a vector. And so we can add vectors just like, you know, we get those things. We can work with them just like we do any other vectors that we have. In every case of this, we're going to have conservation of momentum unless we've got external forces. So we're going to say it's conserved. And they give you a couple examples. You know, even if we're talking about atomic nuclei undergoing radioactive decay, you know, breaks down, parts fall apart, you know, the overall system stayed the same. Or if you have two cars that collide, you know, here's this car going this way, another car going this way, and they run into each other. If we talk about the overall, you know, between those two cars, the momentum they had before the collision is going to be the same as the momentum they have after the collision, unless we have an outside force. Now, the outside force could be friction, so that's why they'll eventually stop. You know, if two rockets ran into each other out in space, they would keep going. You know, another example, if stars explode or anything explodes, a bomb explodes, the overall momentum of that whole system is the same as what it was before. All right, Newton's second law states that if no net force is exerted on a system, no acceleration occurs. Does it follow that no change in momentum occurs? No acceleration. If we have no acceleration, do we have a change in velocity? So the answer is yes, because there's no acceleration means that no change in velocity, therefore no change in momentum. You know, another line of reasoning is simply that no net force means there's no net impulse, and thus no change in momentum. Once again, it has to come from outside the system.